Welcome to CSC 201, Lesson 9.2, Possibility Trees and the Multiplication Rule. The multiplication rule is a quick way to determine the total number of possible outcomes of an experiment without drawing a possibility tree. That is, it's a quick way of finding the number of elements in a sample space without having to list them all. So here it is. The multiplication rule says that if an operation consists of k steps and the first step can be performed in n1 ways and the second step can be performed in n2 ways, etc., the kth step can be performed in nk ways, then the entire operation can be performed in n1 times n2 times ... nk ways. So how many possible outcomes are there when you roll two six-sided dice? First, I want to use the multiplication rule to answer the question. So I have two operations. Roll the dice once, roll the dice twice. Or roll the first dice, roll the second dice. So all I have to do is multiply the outcomes of each of the two operations, or each of the two steps. So I have roll 1 here, and I have roll 2 here, and I have to multiply them. So how many possible outcomes are there when you roll a six-sided dice? 6. And the other next dice also has 6 options. You multiply them together and you get 36 possible pairings for when you roll the 6 dice, the 2 dice. We want to verify this with a possibility tree, which is a little messy, but we're going to try. Okay, let's see. So here's the root of my tree. When I roll the first dice, there are 6 options. 1, 2, 3, 4, 5, 6 options. Okay, so when you roll a dice, you can get a number from 1 to 6. And then after you've rolled the dice once, you roll the second dice, and there are again the same 6 options. So after each of these, I want to put 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so there's my possibility tree. How many possibilities are there? Well, we just have to count up the branches. So I've got 1, 2, 3, 4, 5, 6. So each of my main 6 branches has 6 branches off of it. So I have 6 sets of 6, so 36 branches. That's where the multiplication rule comes from. 36 branches. All right, so let's suppose 4 members of a committee must be assigned to the roles of president, vice president, secretary, and treasurer. There's only 4 people on the committee, and they each have to take one of these jobs. How many different permutations are possible? So how many different ways can I choose president, vice president, secretary, and treasurer? How many different orders can I create? Well, I have to choose a president. I have to choose a VP. I have to choose a secretary, and I have to choose a treasurer. Now, when I choose president, let's just, without loss of generality, assume we choose the president first. How many options are there when we choose the president? There are 4, because there are 4 members of the committee. All right, so I've chosen 1. That's the first step in my process. Next step is to choose the vice president. How many options do I have? Well, 1 person is out of the running because they've already been chosen for president. So there are 3 left to choose for vice president. And then once you've chosen both president and vice president, there are 2 people who can become secretary. And then there's only 1 person left who has to become treasurer. And we multiply these, the multiplication rule, because they are just steps in a process. Multiply each of those together. 4 times 3 times 2 times 1. That's known as 4 factorial, which is 24. So in general, for any integer n with n greater than or equal to 1, the number of permutations of a set, that's how many ways you can rearrange the order of the set, is n factorial. So slight variation, suppose you have a committee of 10 people and we have to select 4 of them to be president, vice president, secretary, and treasurer. How many possibilities are there to choose the 4 committee roles? So I have president, vice president, secretary, treasurer again. But now when I choose the president, I have 10 people to choose from. When I choose the vice president, I don't have all 10 because one of them's president now, so I have 9. Then I have 8 people, and then I have 7 people. So when I multiply those, I get 5,040 possibilities for choosing a board, president, vice president, secretary, and treasurer out of 10 people. In the previous example, we were creating a 4 permutation of a set of 10 elements. So that's just the language we use to describe that. A 4 permutation of a set of 10 elements. So how many ways can we order, different ways can we create an ordered set of 4 out of a set of 10? And we denote it P 10, 4. Permutations, 10 elements, choose 4 of them. So in general, this is the way you calculate it. It's this formula P n, r. It's just n times n minus 1 times n minus 2 down to n minus r plus 2, which feels a little messy. So I like this one myself, and I'll show you that with the example we just did, you get the same answer. So remember that our answer previous in the example, the answer was 10 times 9 times 8 times 7. And we were doing P 10, 4. So that means you start with 10 and then you start writing the factorial, but you only write down 4 numbers. Okay, so 10 times 9 times 8 times 7. But this captures that same thing via canceling. So n factorial, that would be, so if I do P 10, 4, that should be 10 factorial over 10 minus 4 factorial. So 10 factorial over 6 factorial. And 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 6 factorial, over 6 factorial. And your 6 factorials cancel, and you get the same thing that we got just by thinking it through. So this formula captures the process that we used in the example. So let's suppose a certain combination lock requires you to choose 3 numbers, each from 1 to 25. How many different combinations are possible? So I have 3 choices to make. First number, the second number, and the third number. Each of them I get to choose from 1 to 25. So I have 25 ways of choosing the first number, 25 ways to choose the second, and 25 ways to choose the third. And that comes out to 15,625 possible combinations. And let's suppose the locks are constructed in such a way that no number may be used twice. How many different combinations are possible? So now I just can't repeat a number. So I have the first number, the second number, and the third number. When I choose the first number, I have 25 options. And when I choose the second number, I can't repeat the first, so I only have 24 options left. And when I choose the third number, I can't repeat the first or the second, so I only have 23 options. We multiply these together, and we get 13,800 combinations. Okay, so we'll finish this lesson with a little proof that every integer greater than or equal to 2, for every integer greater than or equal to 2, the number of permutations, the number of 2 permutations of a set n plus the number of 1 permutations of a set n will always be n squared. So let's just calculate each of these. P of n comma 2. So that's like you have a committee of n people. How many ways can you choose 2 of them to be president and vice president? Okay, so the formula for this is n factorial over n minus 2 factorial. I'm just applying this formula right here. For P of n comma r, I'm replacing the r with a 2, but the n is staying n. Okay, so this is n factorial over n minus 2 factorial. And then I'll simplify this. N factorial means n times n minus 1 times n minus 2 down to down to 1. You know what? I'll write it out. Times n minus 3 times n minus 4. And you just keep going. You keep taking 1 away from whatever n is. Like if n were 10, then this would be 10 times 9 times 8 times 7 times 6. And I would keep going until I got to times 2 times 1. And then n minus 2 factorial, you start with n minus 2. And you keep decreasing by 1. That's what factorial means. Keep going down by 1 until you get to times 2 times 1. So then I get some cancellations here. N minus 2 down to 1, n minus 2 down to 1, and this is just n squared minus n. I just distributed this n times the n minus 1, n squared minus n. And then let's do a similar calculation for p n comma 1. And we have n factorial over n minus 1 factorial. And this is n times n minus 1 times n minus 2. Keep going till you get times 2 times 1. And n minus 1 factorial is n minus 1 times n minus 2, all the way till you get 2 times 2 times 1. And we have these cancel on the top and the bottom, and we just get n. So what I'm trying to prove is Pn2 plus Pn1 equals n squared. So let's add Pn2 plus Pn1. So Pn2, I got n squared minus n, and Pn1, I got n, and I have a minus n and a plus n, and that just gives me n squared.